Well, in this lecture we shall be talking about so called arithmetic pipelines. Now, in a computer system, if you see the way pipelines are used or utilized, you will find that they are used in broadly two areas or in two ways. One, to speed up the execution of the instructions, that is called instruction pipelining, and second, to speed up the arithmetic operations, that is called so called arithmetic pipelining. So, today in this lecture we shall be looking at some examples of design of arithmetic pipelines. Okay. So, let us see. So, we start with a very simple example. Well, we have already studied fixed point addition. We have seen how a ripple carry adder works. So, in a ripple carry adder, we use a cascade of full adders. So, every full adder is carrying out the addition of a pair of bits. It generates a sum, it also generates a carry, and the carry goes to the input to the next stage. So, this carry ripples like this, that is why the name is a ripple carry adder, right. So, earlier we have seen that due to the rippling nature of the carry, the performance of a ripple carry adder is not so good. The worst case delay is pretty high in fact. So, it has a bad worst case performance. But now let us see, can we use pipelining to improve the performance of a ripple carry adder? Let us see. Well, one assumption we shall make, well, we shall be requiring latch or registers if we want to make a pipeline. Okay. So, our assumption is that the delay of a latch will be comparable with the delay of a full adder. Okay. Fine. Let us see. This is the full adder design that we have seen earlier. This is the example of a 4-bit ripple carry adder, 4-bit ripple carry adder in fact, parallel adder. There are 4 full adders. As I said, each of the full adders will be adding a pair of bits of the input numbers A and B, generating the sum bit and generating the carry bit for the next stage. So, worst case delay will be the first full adder will be generating a carry, because of that this carry will be generated, because of that this carry will be generated, and again this carry will be generated. So, 4 multiplied by carry generation time in full adder, this will be roughly the worst case delay. Of course, there will be one more because of the sum generation. Anyway, I am looking at the carry only. So, roughly speaking, because it is a 4-bit ripple carry adder, the worst case delay will be 4 times the carry generation time of a single full adder. Now, let us try to do one thing, let us try to stretch this ripple carry adder in a skewed way. So, that in the different time steps, let us move the different stages of the ripple carry adder, the different full adders in the different time steps. Let us make them different stages in the pipeline. So, what we are doing is that whatever ripple carry adder was here like this, we are making it like this, we are stretching it. You see, you just ignore this pink boxes for the time being. You see that the full adder is still a full adder, okay. But what I have done is that we have drawn it in a skewed way, and these are the 4 stages of the pipeline you are defining, and the small pink boxes will be our latches. See, in the first stage only the last full adder will be working, and the other input bit pairs which are coming, they will be simply stored in the latches, they will be used later, not now. After the first stage is finished, this carry C1 has been generated, they will be stored in this latch, and the sum will be stored here. So, now stage 2 comes into the picture. In stage 2 only the second full adder is active, the others are simply dummy, these values are copied into the next latches simply, this sum is copied. Okay. So, again this carry is copied, this sum is copied. In the third stage again there is a full adder here, the sums are copied, these bits are copied, and in the last stage there is a full adder. So, you see, of course, we are using many latches, but when the input data is transferred to the second stage, we can parallelly feed the next set of data to the first stage. So, there can be the possibility of overlapped execution, okay, just like in a pipeline, right. This is the advantage we gain here. So, a simple calculation. So, if we just assume that the delay of a full adder is TFA and a delay of a latch is TL. So, the clock period has to be greater than equal to this full adder delay plus latch delay. So, after the pipeline is full, we can expect one result in every time t. See, earlier in a full adder, roughly we are getting one result every time 4 into delay of a full adder for a 4-bit adder, but now in the pipeline implementation we will be getting an output, one output every clock cycle, right, that is the advantage. So, suppose I have a program like this where I am doing some addition a large number of times, let us say there are 10,000 additions. So, I can use this kind of a pipeline to advantage. So, after my pipe is full, I can get one output every cycle, right, instead of waiting for, means one addition to be complete before starting the next addition. If you have a pipeline, it can definitely give you speed up for this kind of vector, you can say vector arithmetic operations. See, for individual arithmetic operations addition, your pipeline will not give you any benefit, but if you have a large set of data, large number of data like 2 arrays you are adding, like in the example I have shown, the array B and C you are adding to generate the result array A. So, just like this, if you are adding 2 arrays and the numbers of the elements are being fed to the pipeline in sequence one by one, there this kind of arithmetic pipeline can be used to benefit. So, basically wherever there is something called vector kind of arithmetic, vector processing, pipelining can give you great benefit. Okay. This again we shall come back later. Okay. Let us now come back to floating point arithmetic, that how it can be pipelined. Let us look at floating point addition. So, this we have already seen in detail earlier. Floating point addition requires the steps of comparison of exponents and alignment of mantissa, this is the first step, then addition of mantissas, normalization of the result, and because of normalization you may need to adjust the exponent. Subtraction will be very similar, and so instead of addition you will be subtracting. So, just an example for 2 decimal numbers are shown here. Suppose I have 2 numbers a and b, because the exponents are different 2 and 3, I make the second one also 3, I means alignment of mantissa, 0.8200 I make 0.0820, such that this also becomes 10 to the power 3. This is called alignment of mantissa. After alignment I add 0.9504 and 0.0820, I get this. Let us say normalization means it starts with 0. So, here I do a normalization, that means I shift right by one position. So, exponent was 3, but because I have shifted right, I have to adjust the exponent, I have to make it 4. So, my final result will be this into 10 to the power 4. Okay. So, these steps can easily be mapped into the various pipeline stages. This is the floating point addition hardware which we saw earlier. This is the non-pipelined version. So, just a quick recap, the 2 numbers to be added were here, sign, exponent and the mantissa or the fraction. First, we are comparing the exponent by using a subtraction, using a small ALU, and after subtraction you see the difference in the exponents. We will have to shift the smaller number fraction by that many bits. So, there will be a shifter. After shifting, so there will be multiplexer to select the correct fraction. There is an ALU which will be carrying out addition, and after addition you will have to do normalization. You will have to check whether you have to do increment or decrement accordingly shifting left or right, and for the IEEE format you may have to do a rounding in the last step. So, that step is also shown. This already we have seen earlier. Okay. Now, these basic steps you can easily break into a pipeline as a pipeline stage. So, I am showing one simple implementation of a pipeline like this. Let us say the two numbers are a into 2 to the power p and b into 2 to the power q. So, here I am not showing the sign, just the mantissa and the exponent. This is p and this is a, this is q and this is b. So, in the first stage S1, I am comparing the exponent, there is an exponent subtractor. So, this p is coming and this q is coming, that is subtracting. So, the output will be r, which will be means after subtracting you will be know that means how much, means which one is the greater, that also is known, that means r is the greater of the two, p or q, that also is known. And after doing this you select the fraction which one is smaller. So, either a or b, one of them is selected, and after subtraction whatever is the result, that many time p minus q, these many positions you are doing a right shift. This is your mantissa alignment. So, after mantissa alignment you take the other fraction here and this shifted fraction here, you do an addition. In stage S2 you are adding the mantissas. In stage S3 after adding you will have to do a normalization. You will have to have a circuit which will count the number of leading zeros, and depending on that it will be shifting the mantissa left by that many positions. This is stage S3, and depending on how many positions you have shifted, your exponent will have to be added by that number. So, this exponent correction. Well, here I am not showing normalization, just simple floating point addition as a pipeline, and these small rectangular boxes are the latches. So, finally, you get the result and it is a 4 stage simple pipeline. Okay. Fine. Now, if we come to floating point multiplication, multiplication is a little simpler, because here you do not need to align the mantissas before the operation. You simply add the exponents and multiply the mantissas, then normalize. Like if you have two numbers like this, you add the exponents 3 plus 2, 5, you multiply the mantissas straight away, it is 0.7793, it is already normalized, no change. So, your result is this into 10 to the power 5. Division is simpler, is similar to multiplication. So, here you will be doing subtraction, here you will be doing division. And again for IEEE format, at the end you may need a step of rounding, right. So, for multiplication and division, we shall see how we can, means we have already seen earlier how we can implement that. Now, we are seeing a multifunction pipeline for addition and multiplication together. Let us see, because already we have seen nonlinear pipelines earlier in our last lecture. This is a simple pipeline for floating point multiply. So, I am showing a simplified diagram. You are doing add exponents, multiply mantissa, normalize, rounding. But the thing is that when I am saying this add exponents, multiply mantissa for example, or normalize, these may require multiple steps, because multiplication and addition are not of the same complexity. Multiplication takes more time than addition, right. You may have to compute the partial products, then add them. It may need multiple clock cycles. So, a technically more correct visualization will be something like this. Multiply mantissa, you can break it up into two boxes. One is the generation of partial products, this also will be an iterative process, and for every iteration you will be doing an addition, you will be accumulating the partial result, partial sum. Okay. So, both these two stages may be required to execute it for multiple clock cycles, and normalize and rounding, and at the end you may need to do a renormalizations after rounding, because the number might become again unnormalized, right. Fine. So, this is a more technically correct version of a floating point multiply pipeline with the IEEE format, because for IEEE format you need this last step. And if you look at the floating point add, for floating point add you need a mantissa alignment initially. So, for mantissa alignment you have to shift the mantissa certain number of times. So, this again can be an iterative step. After this shifting, then you do an addition, you find the number of leading ones, then you will have to do a right shift or left shift here, left shift by that many position. This also can require multiple number of cycles, then rounding, and for IEEE format renormalize. So, you see with respect to the previous diagram, there are some similarities, okay. Some are different, some are similar. So, we can combine both the two diagrams into a single pipeline like this. This is a combined adder and multiplier. You see, this partial shift will be required for addition, partial product will be required for multiplication, but for both these cases mantissa addition is required. Similarly, partial shift will be required for again addition, right. But for multiplication you can straight away go from add mantissa to renormalize, you can skip these two steps, because leading one and partial shift will be required only for addition. For multiplication you can straight away skip G and H, you can straight away come to D here, right. So, if you have a multifunction pipeline like this, I am not going into much detail on this, I am just giving an idea. Then you can similarly you can construct the reservation tables for addition and multiplication operations. Like here for multiply operations, you will be needing A, B, C, D and E. You will be needing A, B, C, D and E. Here what we are saying is that steps B and step C will be requiring little more time. We are seeing that it is taking 2 time steps, because partial shifting or the partial products and the add mantissa, this will take more time, right. Because of that, I am assuming that the stages B and C are being used for extended period. So, for this reservation table you see that the forbidden latencies are 1 and 2. So, the collision vector will be this. So, naturally intuitively you can say that your minimum average latency will be 3, because 1 and 2 are both forbidden. So, 3 we can use definitely. Yeah, it is true, 3 is permissible latency that you can use. So, let us see, for latency 1 there will be a collision. You see this was the reservation table, right. So, this x is the first data. Suppose I am feeding the second data, I means after one cycle. Okay. So, z has shifted here, z has shifted here, z has shifted. You see x and z will collide in B and C. So, latency 1 will lead to a collision. So, x and z refer to 2 consecutive data items which are fed. Okay. Z is fed earlier, X is fed now. Now, if I use latency 2, that will also lead to a collision. You see Z is now here. So, after 2 steps I have fed Z, no, Z was there, after 2 steps I have fed X, it was fine, but only at the last stage in D there is a collision. So, 2 is also not allowed, and as I said, with latency 3 you can use it very clearly, there is no collision anywhere. So, for multiplication you can feed the data with a latency of 3 without any problem. Similarly, for addition, the reservation table will look like this. So, here again this F and H are being used extended period. Here there is only one forbidden latency 1. So, here minimum average latency will naturally be equal to 2. So, here you can similarly justify that. So, to summarize, this arithmetic pipeline is a very standard feature in modern day processors. So, we shall see later in some detail about vector processors. Vector processors are computer systems which are specifically designed to operate on vectors of data very fast. Okay, we shall of course first be discussing later in the next week that how we can build or how we can convert our MIPS architecture that we have seen earlier into a pipeline, how we can execute the instructions faster. But then we shall see that how we can also augment that pipeline with arithmetic pipeline concepts, so that vector arithmetic operations can also be sped up. What we have seen today, we have seen some very simple examples of some arithmetic pipelines and one instance of a multifunction pipeline, multiplier and adder together, where we have seen that we can speed up operations by implementing the arithmetic circuits as a pipeline, provided we have continuous stream of data to be fed to that pipeline. Okay. That is possible only if we have vectors of data to be operated on. All right. So, we shall see the impact of arithmetic pipeline. We shall see later that the arithmetic pipeline can complicate that the design of the MIPS 32 pipeline, but this we shall be seeing only later. Okay. So, with this we come to the end of this lecture. So, there are a few things we shall be discussing after this. You see, means we shall be looking at the input output process in a computer system, how peripheral devices are interfaced to a computer system, what are the different characteristics of the peripheral devices that makes their interfacing somewhat more complicated or complex as compared to interface memory devices. And also we shall be looking at some of the commonly used bus standards that we see everywhere today. And of course, after that we shall be looking at how we can make our computers faster by incorporating pipeline at the instruction level and also, as I said, at the arithmetic level. So, with this we stop for today. Thank you.